So now, as I said before, like you really shouldn't be going looking at this video until you've tried it yourself. But anyway, that's kind of a more ye problem. So we're going to finish this off. So this one we do Euler's method on the v. So it should be the previous plus the step size times the derivative of v, which I'd written down the last day, was minus 5 over 2, which is minus 2.5 times v, but it should be the previous v, and minus 6 over 2, which is 3 times the previous x. And then I can select these two, and let's see what we get. Something like this. So this is GoAU, damped harmonic oscillator. What's happening? So the door, now actually for later on I'm going to actually plot the force, which should be interesting. I might have to multiply it by something to make sure the scale is good. So the force is equal to the mass times acceleration. Oh, in the previous video I was talking about dividing by m. You don't have to do that. So it should be equal to minus lambda, which is 5 times v, minus 6 times x. So if we plot all of these, let's see what happens. Yeah, the force is cool there. I'll leave it there. Right. Damped harmonic oscillator. So, do you know what I'm going to do? Well, I'm just going to pause and get a better grip. There, look, it's fine. So, what we have is that when the initial displacement is big, it's 1. Then the force is trying to pull it back. The spring force is coming into play, and it's very, very strong. And what happens is the force, then what happens is, what's happening? So say you get up to here, right? And there's still a displacement, but there's also a velocity. And the velocity is negative. Actually, I'm not sure what I'm talking about here, but I want to say that when the displacement gets smaller, but the velocity gets bigger, what happens to the force? I suppose maybe we're looking here where the force is absolutely 0. So this is the point where you've got the spring force, which is pulling, is being balanced by the damping force. And the spring force is only getting smaller at this point. Now the spring force is proportional to the displacement, so we can see that. But what happens is that the force then, the damping force becomes bigger. So what we see is kind of after this point, if I make this a bit bigger, so I think we see that, so see here, so after that, the damping force is going to be bigger. And so the displacement is small, but the speed is big. And so that's when the damper really kicks into play, and it slows it down. It decreases the speed. And you get this kind of behavior. You change the values of k and lambda, and you see the different behaviors. Can we maybe, so one behavior would be, so maybe I'll make this divided by 2. Say if it was 5 over 2. And this was 6 over 2. And this is 5 and 6. Okay, so I'm gonna do a little bit of stuff here. So k and lambda. So I can do that here. I can just use the dollars. So this is the k, isn't it? So dollar row, it's going to be row 2, column 6. What am I talking about? F6. It should be $6, isn't it? Yeah. And then the other one, no, not F6, F2. And then the other one is, I have them mixed up, don't I? So this should be G, this should be $F$2. Yeah. So k equal to say 5 lambda equals 6. Okay. Put that down, that's no problem. That It's gone back, reverse it. Now here I need to put in, this is the K, this is the lambda. Dollar G $2. This is the K, dollar F $2. The dollar means it won't change when I pull it down. And here it doesn't come into, okay, so now I can take all these down. So now I can adjust these. So for example, if I make the spring too strong, I get oscillations. Now the force is too big, so I need to divide the force by something to make it kind of not so big. So let's divide the force by 10 so we can get a better look at the graph. You know what I mean? So here we see the displacement. So this is underdamped. The damping is too small. And what's happening is when the force, so when the displacement here is still quite big, the velocity is big, but the damping is not strong enough to slow down the oscillator and stop it before it reaches equilibrium. So you get these oscillations. On the other hand, if you make, so I'll put them here like this, if you make the lambda too big, it just takes so long. Maybe that's too big. It's taking ages. So this is like the door that starts closing and it creaks and closes. And then you have critical damping, which is when it kind of closes quite quickly. Now I've got a mass equal to 2 here, so I just have to do some little sums for myself. I'll have to pause it. This is the magic number. You get critical damping. So what critical damping is basically at the point here, well, I won't go into it, but you can see it's much better. Like, so if you make the spring, if you make the damping stronger, it takes too long. If you make the damping 12, it's just right. If you make the damping smaller, you get oscillations. So the critical damping is the least amount of damping that will stop oscillations. It's basically the way I think about it. Okay, that's long enough on that, but it's kind of cool. Right, now we need to do this one. So this is more about coding. So define variables. Okay, so let's say, now we're going to go, I think, with the vold. Actually, I'm not going to do the vold. I like taking it from the worksheet. So dim dblt as double, dim dblx as double, dim dblv as double. After that, dim dblh as double. I think there's ways of kind of doing this a bit faster. dbl ft for final time as double. Dim dbl, I could do just a big L, maybe a bit easier, isn't it? As double. Dim dbl m as double. Dim dbl k as double. And then dim int row as integer. Plenty of variables there. Initial values. So we've done a few of them and the rest. So t done xv final time dbl final time equals cells row 2 column 6. dbl h I forgot equal to cells 2 5. dbl l equal to cells 2 7. dbl m equal to cells 2 8. dblk equal to cells 2 9. And int row, we're going to start in row 2. Okay. What about our loop? Do, so print these. Cells int row column 1 to be the time. Cells int row column 2 to be the displacement. Cells int row 3 to be the velocity. I'm not going to do the old like that. Calculate the next t, next v. Okay. So we'll do first next v. dblt is equal to dblt plus the step size. And now we'll do the v. dBLV is equal to dBLV plus step size dBLH times the derivative of v, which is minus lambda over n times v minus k over n. Times x, happy days. Now, in the next one, we have to be careful. dBLX is equal to dBLX plus dBLH. And now I get the previous v from here. So that's us taking you, and then loop until, oh, forgot the intro. That's why you save before you run. Intro is equal to intro plus 1, and then great. So loop until the time is bigger than the final time. So very important, save before you run. Okay, so hopefully all goes well. Variable not defined, that's why we do option explicit. I'm tired again, the baby. Didn't like that. Try again. Variable not defined. That's what your option explicit is for. There we go. Give it a plot. Lovely. Now what we want to do is I've put in some code for selecting things, so you can record a macro. I seem to have done a different option here, which is kind of nice. Although you still want to, yeah, I'll record a macro, so we'll just do that now. How do I do that? Record macro. So delete calls. Select them, right click delete, TXV, stop recording, into our thing. I just have to remember the name, call, delete, calls. We can do that up here, because I want to run this multiple times. Right. So in particular, I might be interested in a bigger final time. Now here you see the graph isn't doing great for us. So dealing with putting in the graph is something for you. Okay, so we can kind of play around now, and now we do have the issue where, okay, I'll just show you one option for the graph, so you get an automatic graph that works well. The problem is you're going to have loads of graphs on top of each other. It is possible to delete them. I think I have it. Maybe if I just chart. Yeah, here we go. We'll just wrap this. So this is, I think this might be helpful to your thing. So this is going to delete previous graphs. And now what we can do is we can go down the bottom of this and put in a record macro to select the first 3 columns and insert a graph. And we won't have that problem I was talking about. Well, I hope this works anyway. So this is insert graph. Right, so what do we say? Select all these, insert graph. It's in a nice place. Look, I have to throw an automatic oscillator here. Oh, do I have to do record macro? Yeah, sorry, what am I doing? Call, see all that did. all that code generated, and record macro is mighty. Do it down the bottom here. Call that. Now hopefully this works. Yeah, so it's going to delete the previous one. So remember, if you went to a much bigger time before, it wouldn't work very well. Or say if we come back, so you're getting something that's really nice there, and then you can kind of play, no bother, change the step size, getting more accurate, change the amplitude, no bother. I think this is great crack. And the thing about these, of course, you do know the exact answer. Now, maybe the other, okay, so maybe we pick a big enough time and we look at some critical damping issues. I think the easiest critical damping C with mass equal to 1. So it's when the auxiliary equation is repeated roots. So you're looking for b squared minus 4ac to be 0. So the easiest way there would be to put lambda to be like twice something, so 6, and then the k to be 9, and you're going to see critical damping. Now that time is way too much, so we'll go to 5. Now look at what happens when we make the damper a bit stronger. Even 6.5, does that make a big difference? Not that much. If you go to 8, it takes ages. If you go less than 6, you're going to get oscillations. I think it's cool enough. Right. And then I think we have to do the Heun one. Oh god, where are we gone? So damped, or if I think maybe external force, I've lost the page. There we go. Right, so I'm going to go fairly quick here. I will look at the additional stuff. So what have we got to do here? We need a panel. Let's just route this panel. Starting at E. Now I probably need to go up to F. Yeah, that was handy, wasn't it? I can rob some of the code, but we'll see how far we go. More VBA. I am going to copy and paste. I just have to be very careful now because like things are one bit over. In fact, I'm even going to undo that just so I can. Okay, so what's missing here is I can leave the deleting the columns, although I'll have to do a new one because I think I'm eventually going to plot the force as well. And I might even include an external force, but we'll worry about that later. I will keep that there. I need predictors. Right. Initial values. Predictors don't need initial values. They don't need to be plotted. So the only thing we're missing here is the predictors. So let's do and you do the predictors at the same time. dBl prid equal the previous v value plus step size times. And we can just use this. dBl x predictor is equal to dBl x. It's basically this, isn't it? Now we don't have the problem that we had with the old variable here yet. So what I can actually do is I'll explain why in a minute. So the derivative of x is dBlv. So I haven't calculated new v, I've calculated v predictors, so there's no problem here. Now I'm doing Heun. So these are the Euler predictors. And then here you're doing the Heun. So this looks good. Now I need to do two slopes and average them out. Now brackets are going to be your enemy. So put a big bracket around that. Plus you need another slope. Now I'm just going to copy and paste this. This is a slope. This is another slope, and I need to divide all of that by 2. Now, you can have issues with BOMDAS. I'll give you a hint here or something useful. If you go to Maths Online and you go to, so that's something in Canvas, and if you go to units and you do Control F, search the page for Maple, you can download this mathematical software. Now, I'm not saying that you can use this quite so easily, but what am I looking at? What it is useful for is finding, like it's very hard to see is there a BEMDAS error here. So what I can do is I can just copy this, put it in here, press enter, and it'll kind of show me, look, I have done, now there's a cancellation, but we won't worry about that, but I have done 2 slopes divided by 2 to step size, so there's no bendless error. So that's a little hint for you, or an option. So this one should be the previous, so this is okay. And then this is the next predicted. So this should be, so this was the first slope, where we are, and then this is the slope at the predicted next point. So, that's better. And now we need to do also Heun's method for the x, but you could actually do Euler for just x or something like that. So we do dBLV, that's the previous slope, plus the predicted next slope. Oh no, sorry, dBLV has changed. I have to use the printed version. So that's the previous slope. And then the predicted next slope would be dBLV predicted. And I think, no, I can't do these because I'm going to do some additional functionality in a moment. Right, so let's look at this. What's the additional functionality? Include plotting the force. I think that's cool, so I'm going to do that one. So how am I going to do that? So I'm going to do that by just printing directly here. I don't need a variable because it's just minus lambda v minus kx. So cells intro 4 is equal to the damping force, which is minus dBl lambda times dBl v minus dBl k times dBl x. So that's going to print that. I want to do remember the macros I had. Now you could come in and just delete them, but I think it's probably safer to do new macros. I need 2 of them. I need insert delete cols 2. So that's the one I'm going to select all them, delete. I'm going to put in T, X, V, F for force. And I'm going to do that. I'm going to do all that. Sure, I may as well. Stop recording. I should run it, although I have no button, which would have been nice. Oh, I want a button. So how I can do that is as follows. It seems to have done it for me. Didn't it? Happy days. Yeah, seems no issue there. So I'm going to save there and I'm going to run mighty. So I want to do, now this force looks too big, so let's do force divided by 10. View code. So divide the force by 10. Because the units are, like you're comparing stuff, it's not going well. Did I do the insert the graphs? Oh yeah, no, I'll do delete cols. And after that now I'm going to write the macro to plot this. So select all of these, insert, run this yoke. Now the force is still quite big there. Look, what can we do? Damped harmonic oscillator. You could do something where you could be very clever actually, and I think I will be very clever. Well, I need to stop recording, don't I? Or I need to start recording. That was stupid, sorry. Record macro. Insert graph 2. Select all these yokes. Insert graph. Whoop. Damped harmonic oscillator. Now I think what could be cool could be to put that in the code at the end as a call insert graph 2. I can just double check here to make sure it is the right name. Insert graph 2, yeah. So the thing is I'd look at the force. So it must have been initially, did I divide it? Yeah, it's divided by 2, but it's still quite big. So what I could do is I can make the initial force maybe to be the same size as this. So what I could do is I could take the force, I'm trying to make it so that it has, so that that basically it has the same magnitude as the acceleration. So I'll just write down F divided by some, now what's the name for this thing? Alpha. So I'm going to divide the force by something to get A. And is this any good to me? I have to pause to think, I'm afraid, and I'm running out. But it should be possible to divide alpha by F by something. So the alpha actually should be the force divided by the acceleration. Sorry, by the amplitude. But I'm kind of drawing a blank here. So maybe we can just calculate on the very first go the alpha. This is possibly overthinking it now. dBl alpha as double. Okay. So what I want to do here is I want to calculate that to be, I've done my little sum, dBl alpha is equal to, I want it to be the initial force, which is this. Divided by the initial x. And then I want to plot, I think this should make, like this should make this -2. Or 2, that's not, okay, I don't want to make it from positive to negative, so I need to make this absolute value. Does it do absolute value? Oh, look at that. So this is F divided by something alpha. That makes, you see, it's not going to be too big. Like, so if I change the amplitude here to 5, the force will start at 5 as well. So everything will be more in proportion. And you can play around with this. You can add external forces and stuff. But how to add an external force? I'll do one of them here. Would be to, you'd have to look at the dv dt and you go back to the start. So it'd be a plus F force over M. Now let me do what's an interesting force? So it has to go in here. Plus, so I just go write F over M. It goes in there. Time squared, time squared, exponential, drawing a blank here, let's say, I don't know, is it, oh, it does take sine. So let's say sine 0.1 t. Okay, and t is the time. So this is my force. Now I've got an issue, I have to use the previous time. So I take it from here. Possibly complicating things. Now this is the predicted next one, so this should actually be dBlt, because it should be what's predicted to be at the next point. And then this should be, yeah, hopefully everything runs out. Now I'm missing the external force out of, actually we'll throw in that as well, plus, of course I have an M everywhere. So hopefully this isn't making it more complicated. Oh yeah, this is wrong. Pay now if everything went wrong after all this. If you're still here, fair play to you. So this one has possibly gone in, it's gone in between the two of them, but it should be okay. All right. Hopefully this works. Now this is an external force. And what you should expect is eventually the energy in terms of the damped harmonic oscillator dissipates because the damping force is non-conservative. And so what you're eventually going to get is that it's just going to look like the sine wave. That's not happening here because of the numbers that we're choosing. The external force isn't that big. I'm not going to go back and change everything. And I want to see those oscillations. Oh, they're just very, very slow. There. Right. So you see the bit in the very small time, all the energy is being taken out. If I make the damping a bit weaker, that will take more time. And eventually what happens is the behavior is it just mimics the external force. Okay, so hopefully you learned a few things there beyond even VBA.